We are going to take what we just learned in the previous lecture and apply that to number 27. The decomposition reaction of N2O5 and carbon tetrachloride is this reaction right here. The rate law is first order. That's the exponential value on N2O5. At 74 degrees, the rate constant is this value. The units for the rate constants change all the time, so don't get too attached to the units on the rate constant. But this happens to be the value, so good to go. The first question is write the rate law for the reaction, or the first statement is write the rate law for the reaction. So when you're writing rate laws, the only thing that matters is the reactants. Products, don't worry about it all. So every single time, no matter what, we start off and we write this. It's a lowercase k. My k's always look the same. They all look usually like uppercase, but lowercase k. So every time we start off with this, and then the bracket, and whatever reactants we happen to have, it tells us it's first order. You can write the one up here just to show that you have mentioned it, but you don't necessarily need to. It's kind of implied the fact that you wrote it, that it's at least one. Now, if it's zero order, I probably should put a little zero up there, or maybe not even include it at all. But it's probably best to write it up in there so you can account for it. Okay, what is the rate of reaction when I have a concentration for this? So pretty much here, we're just run the math. I have this number I can put in place here. I have a rate constant, it's right there. Just run it out. So I'm going to write the whole thing just so we can see it. Rate is equal to rate constant 4.82 times 10 to the negative 3. The units are per second. And then to multiply that, I could use brackets or parentheses in this particular example. 0.0240. Molarity. Every time I have the brackets, it is molarity, so I really don't need to put those on there. The brackets imply concentration. So again, I don't really need to put the M in there. The numerical answer is 1.16 times 10 to the negative 4, and the units are molarity per second, which will always be the units. When you have something you're asking for a rate, that implies, when it's asking about the rate of a reaction, you are implying the molarity per seconds. So your units every single time must be molarity per second. Okay, what happens to the rates when the concentration doubles? Well, based upon this being the rate law, if this number is doubled, well, nothing else changes. It's just a direct relationship. So this being first order, it should also double. So I'm not even going to write a math relationship in here. I'm just going to double this value based on what we just discussed. It'd be 2.31 times 10 to the negative 4 molarity per second, based again how this equation is set up. It's to the first power, so if this number is doubled, this will double. What happens to the rate when the concentration is halved? So if I know what this number is again, it's just going to be half that number. So I'll write that in here. It's 5.8 times 10 to the negative 5 molarity per seconds. So that's done. All right, let's bounce back over to some notes. Got a little space left here, so I'll stay on this page. All right. This is figuring out how we get those reaction orders. And this is something that has to be determined experimentally. You can't just look at it and say, oh, the coefficients are this, and I'm going to plug them in there. If we, and this is just added information for now, don't use this really for any understanding yet. If I happen to be told that this reaction is elementary, that I know there's no extra steps here, then we can grab these coefficient values and plug them in for the exponentials. But right now, forget about that. You have to figure it out experimentally. All right, I'm going to write out a system here, and then I'm going to kind of go on to another page here, I think. I'm going to give it some headings. Experiment number, concentration of A, concentration of B, and the initial, which is most important, the initial rate of a reaction. Know that a reaction's speed is always going to be fastest at the very beginning because I have the most stuff available. As the reaction proceeds, the speed of the reaction will slow down because you have less of your reactants available. That makes sense. Okay, experiments 1, 2, and 3. For A, I'm starting off with a concentration of this and a concentration of this for B. Now, like any good reaction, I can only change one variable at a time. So in this case, I'm going to look at keeping A the same, but I'm going to double the concentration of B for that reaction. I know I haven't put these in here. I'll put them in a second. And then for reaction 2, I'm going to keep B the same, and I want to see what happens when I double the concentration for A. And so this is how I'm going to set up the experiment. This is my initial, and then I'm going to change concentrations only for one for each experiment. All right, after I do that, I see how the rates compare. My initial for kind of like a control or something I will compare against. I see that the rate of the reaction is this. Now, when I double the concentration to B, I see that the rate of the reaction changed and became this. And then for experiment 3, when I change the concentration of A, I see that the reaction went this quickly, 8.0 times 10 to the negative 5. Okay, so the question is how can I determine how quickly, or what is the rate law for this particular reaction? So I'm looking at the comparison. So how you would do this is dividing different lines. So for example, if I want to know what's going on with B, first of all, let me just go out and write a rate law for this without any exponential values. Remember, every single time you write this, and I have two reactants, A and B. I didn't bother writing that down. So I have A and I have B. I want to know what these two values are for A and B. So what I'm going to do is divide, if I want to know what's going on with B, I'm going to divide line 2 by line 1. And if I do that, I'm going to get 2. I doubled it. And I'm doing the comparison to the rate. When I divide line 2 by line 1, that also equals 2. Now, as far as exponentially, by changing the concentration exponentially, what did that do to the rate of the reaction? This is pretty straightforward. I think I can figure this out. But if you were doing some algebra-ish kind of stuff, what you could do is take the log of this and figure this out. Now again, I understand this probably isn't necessary to do for this problem here, but if it was more complicated or I got some decimally stuff here, it can get a little more complicated. I could run this here and and get the answer this way. In this particular example, it's 1, and I feel pretty comfortable with that. If I run this exact same process to figure out what's going on with A, I keep B the same, take this divided by this, of course it's still 2, but this time, when I divide this line 3 by line 1, I get 4. So 2 raised to what power is 4? I think that's going to be, whoops, I put it in the wrong spot. You've probably been screaming at me this whole time that I put it in the wrong place. This is 1, and this is 2. Because when I double the concentration for A, this goes up 4 times. So this is raised to the 4th power, and this is raised to the 1st power. Okay, got that taken care of. There's a little bit more to this problem here, but I'm going to carry that into the next lecture.